Okay, is my screen visible to all of you? Yes, is it visible? Yes, Nilesh. Yes, am I audible? Okay, okay, okay. Right. Okay. So this is the last chapter of this subject, refrigeration air conditioning. So in first section we study about the refrigeration system. We started with basics of refrigeration. Then we moved towards the VCRS and VRS system. Then we have seen multi-pressure system, etc., etc. Right. In second section we started with the basics of cyclometry. Then we studied the heating and cooling load calculations. Okay. Now this is the last system, that is air distribution system. Right. So first we will calculate the heating and cooling load acting on the building. Then you will select air conditioning system, right? After selecting air conditioning system, you will prepare a bill of material, purchase the equipment, etc., etc. Now the last step comes into supply the air. Now you have to install the system. Along with air conditioning system, you have to also install the ducts and other components in the building. Ducts are the passageways or the medium for air delivery. Okay, so air flows through ducts into the conditioner environments, and then there are air terminal devices also, like register grills, etc., through which air is passed into the room. So that we'll study today. Okay. So what you see on the screen is an AHU, air handling unit, very commonly used air conditioning system or a device in commercial applications. Okay, so one by one I will explain you what is it. Okay, so this is an AHU. It has a two inlets. One is fresh air inlet, that is ventilated air. Another is return air, right? These two are mixed together adiabatically. So first comes air filter. Air filter will remove the particles or dust from this mixed air. Then this mixed air is passed onto the cooling coil, where it is cooled and dehumidified. In case if it is cooled below requirement, then in some cases it is heated again also. Okay, so it is cooling and dehumidification, and then there is some, if required, heating also is provided. If heating is not provided, heating coil is turned off. Then comes the blower or fan through which the air is passed to the ducts. Then comes this air distribution system. So air distribution systems are ducts, etc., through which it is that mixed air, the cooled and dehumidified air, it is passed to conditioner space. There it takes the cooling load, and it maintains the temperature and humidity conditions at the required level. Some part of it again is taken back through return air duct, and it is mixed with fresh air, and the cycle repeats. Okay. Now in this case, we are going to study what is the air distribution system. So the chief requirements of an air conditioning duct system are: it should convey specified rates of airflow to the prescribed location. So we have seen for thermal comfort, there are four major factors. First is air temperature, second is air relative humidity, third is air quality, and fourth is air movement. So air movement should be proper. असं वाटत नाही की तोंडावर असं वारे लागले, right? We should feel a cool breeze passing through surrounding us, right? It should be economical in combine initial cost, fan operating cost, and cost of building space. Obviously, as a contractor or as a building owner, you want to save your cost on this system. You should not transmit or generate objectionable noise. So vibrations level should be as minimum as possible. So commercially, if you look, ducts are insulated as well as they are provided with soundproof coating. Okay, so there are two types of coatings on duct. One is for restricting heat transfer, another is to cancel the noises. Now what you see is on the screen is a typical air conditioning duct layout. So this is a fan from the AHU, it will supply the air. What you see, these straight lines, these are nothing but ducts. So this duct has various branches because it depends on the structure of the building. Now this building has room 1 here, room 2 here, hall number 3 here, kitchen 5 is here, again lounge 4 is here, etc. etc. So such zones are there in this building. We want to supply the air. Now combine, if you combine the CFM required for each room, right? In you have seen in chapter number 5, we calculate dehumidified air quantity in CFM. If you calculate the required air flow rate for each space, you do the summation, you will get the total CFM required. That is a cubic per feet per minute airflow rate required, you will get. So here, let us say this room number 1 requires 400 CFM of cooled and dehumidified air. This 300, 250, 500 and 150. Combinedly, it will give you 1600 CFM. Now, when you calculate the airflow rates, next step is sizing the duct. So 600 CFM will require larger duct when some amount of airflow is taken out through this branch. Obviously, CFM will decrease by 400, so it will become 1200. So at this junction, we have 1200 CFM. Again, size of the duct will decrease. Again, this part is removed, 650. The remaining 550 is remaining here, right? So again, size of the duct will reduce. Again, at this junction, 300 CFM is removed, so remains 250. So for 250, again, size of the duct will reduce. And finally, we come here at point number 3. So how to design this duct system? What are the methods to design? That we'll see here in this lecture. Okay. So see, there are two things. If the velocity is in the duct is very high. Okay. If the velocity is high, you might have seen in convection, if the velocity is more, heat transfer is more, because with increased heat transfer coefficient H also increases. As velocity increases, heat transfer rate also increases. But if we increase the velocity, in that case, fan power consumption also increases and operating cost increases. So operating cost increases as the velocity increases. Next is velocity is low. तुम्ही असं म्हटलं ठीक आहे velocity नाही, पण जास्त जर फार कमी जर velocity ठेवली, if you keep the velocity below required level, duct size will increase. Okay, and initial cost, आता duct size वाढला म्हणजे त्याला लागणारी मटेरियलची कॉस्ट देखील वाढली, त्याला लागणारी फिटिंगची कॉस्ट देखील वाढली, तर त्या केस मध्ये initial cost देखील वाढेल, right? So if you increase the velocity, fan power will increase. If you decrease the velocity means pressure will increase. For increased pressure, we need higher or larger duct size, and in that case, initial cost of the project will increase. So as a contractor or as a building owner, I have to decide or I have to trade off between operating cost and initial cost. Okay. Now classification of duct. What are the types of ducts? What are the major classification of duct? What are the subparts that we'll see? According to type of air. Okay. According to type of air, there are 3 types: supply air duct, return air duct, and fresh air duct. This is just a labeling. Labeling is given just to know where which is air is passing. Generally, fresh air is indicated by green color, return air is indicated by red color, and supply air is indicated by blue or cyan color. According to pressure in duct, there are again 3 types: low pressure duct. So in case of low pressure duct, static pressure should be less than 50 mm of water gauge. Medium pressure duct, static pressure should be between 50 mm and 150 mm. High pressure duct, static pressure should be above 150 mm of water gauge. Now you may be wondering, sir, what is static pressure, right? So I'll give a very easy example. Suppose you have a balloon. Okay. सुरुवातीला बलून कसा असतो, फ्लॅट असतो, त्यात आपण हवा भरतो आणि आपण त्याचं एंड बांधून टाकतो. त्या केसमध्ये बलूनच्या जो प्रेशर आहे त्याला काय म्हणतात, स्टॅटिक प्रेशर. बलून कुठं उडतोय का, अजून नाही. बलून इज ॲज स्टेशनरी बट इट इज फिल्ड विथ एअर. द प्रेशर एक्झर्टेड बाय internal air on the walls of the balloon, it is called as static pressure. Okay, understanding static pressure. आता मी काय करणार सेकंड केस मध्ये, आय विल रिमूव्ह द नॉट, म्हणजे जी गाठ बांधलेली बलूनची एंडला त्याला तुम्ही काढून टाकणार. काय होतं, एकदम हाय वेलोसिटीना एअर त्यातून बाहेर पडते. सो द प्रेशर अंडर विच दिस एअर मूव्स आउट, दिस प्रेशर इज कॉल्ड एज डायनामिक प्रेशर. Static pressure and dynamic pressure. Third is according to velocity of air. So low velocity duct is, air velocity in duct is up to 600 meter per minute. High velocity duct, in that case velocity is higher, it is higher than 600 meter per minute. Okay, so this is a general classification of duct. What are the duct materials used generally? So see, generally duct, what we see is made up of GI sheet metal, then comes aluminum, then comes resin bonded glass fiber. But as I have seen, most of the ducts are of GI sheet metal, and in some cases they use aluminum also. Okay, wherever you want to do cost cutting, in that case you can go for aluminum. Duct shape. What are the different duct shape? There is a circular duct, right? It is like a pipe. Then there is a rectangular duct. Then there is a square duct. So if you go by theoretical part, theoretical calculations, in that case it is preferred to have square ducts, because square ducts give you aspect ratio of 1. But most of the time putting square duct is not possible. So for that case, rectangular is preferred, and most of the time you will see rectangular ducts in the air conditioning systems. Okay? And very less times people go with circular ducts. Okay, even though it is economical. So what you see here, it is an internal part or layout of duct, it is there. So these are the ducts. So see here, this was the main duct. Again, it has two branches like this one, and another this one. So as there are branches take place, flow rate is decrease. With decreased flow rate, will decrease the size of the duct. So here size of duct is reduced. Then there is no sudden change in direction. असं डायरेक्ट काटा कोणात नाहीये. तिथे आपण काय दिलंय, राउंड शेप दिलेला आहे, because we want to reduce the pressure losses in the duct. Then what you see here is the air terminal device. It is called as, generally the name is air terminal device, and specifically this, it is called as diffuser. This is called as diffuser. This you may have seen in many of the malls or halls, etc. This is called as diffuser. Okay, and these ducts are supported by these hangers. These are called as duct hangers, right? These are vertical bars are there through which we are supporting the duct system. Now what are the pressures in the duct? So three pressures are there. Actually two pressures are there, static pressure and dynamic pressure, and summation of them, it is called as total pressure. Okay, so as I told you before, what is static pressure? So suppose there was a balloon which was flat initially. I will fill this balloon with air, right? Now the air inside will exert some pressure on the walls of the balloon. This pressure, it is called as static pressure. Now I will puncture this balloon and the air will move out with high velocity. This head under which velocity moves out, it is called as dynamic head. Okay, now very important concept is here. If I want to explain this in terms of ducts, suppose there is this duct is there, I'm supplying air into the duct, right? If initially, let us say, okay, initially let us say this was the manometer, just vertical manometer I have connected, right? Suppose this is a sorry, this is the initial manometer I have connected, right? In this it is just straight inserted into the duct. In this case, whatever reading this will give you, this will be static pressure. This will be static pressure. Okay. Now, if I just made this end as curvature like this in the direction of flow of air, in this case, what will happen? Not only static pressure, but also this air will move inside the tube and it will add its dynamic pressure. Okay. So when you make your manometer setting like this, like there is curvature, So whatever reading you will get H in terms of, let us say, mm of mercury. So that will be total pressure, because it will add static pressure as well as dynamic pressure. Okay. Now next is mass balance in ducts. Okay. So we will apply the law of conservation of mass to the ducts. Okay. Now here we are assuming the air is incompressible. Okay. So that means we cannot compress the air, or density of air will not change from point to point. The density will be constant. So applying law of conservation of mass, M1, that is a mass flow rate at inlet 1, equal to mass flow rate at inlet or outlet 2. Okay. So here in this case, we have a duct with a decrease in cross-section area. Initially pressure is P1, velocity V1. Outlet pressure is P2 and velocity is V2. If I apply my law of conservation of mass, in this case, M1 will be equal to M2. Mass flow rate is given as rho AV, density into area into velocity. Because area into velocity gives you volume flow rate meter cube per kg, sorry, meter cube per second, and into density that will give you kg per second. So this is why I will equal here. Density and density term will get cancelled, and I will get A1 B1 equal to A2 B2. So this is a continuity equation. For continuity equation, I am assuming air is incompressible. Okay. Now, if I apply the Bernoulli's equation, right? If I apply the Bernoulli's theorem between 1 and 2, so you know Bernoulli's theorem, P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. Here, P1 by rho g is a pressure head, V1 square by 2g is velocity head or dynamic head in our case, and Z1, Z2 are the elevations. Now in this case, Z1 and Z2 is equal, so that will get cancelled. What you get is here simply this equation, equation number 4. Okay. Now again in this case, I will multiply both sides by rho g, so I will get this equation, and in this case, this equation reduces to P1 plus rho V1 square by 2 equal to P2 plus rho V2 square by 2. Okay, and this term rho V square by 2 is nothing but dynamic head. It is called as dynamic head. So it is just written as P with suffix V1, and this is written as P with suffix V2. This is not PV2, this is P suffix V2. So here PS1 and PS2. So P1 is replaced by PS1, P2 is replaced by PS2. These are static pressure. P1 and PV2 is dynamic pressure. So considering, now next I will consider the what are the pressure, the losses in the system. So considering pressure drop due to friction, bend, fitting, etc., change in shape, I will add that loss to RHS. Okay. So initial total pressure will be equal to final total pressure plus pressure losses. So this is very important equation, equation number 6, right? Okay. So this is a pressure equation for ducts. Total pressure, that is static pressure, dynamic pressure at 1 or at the inlet will be equal to static pressure, dynamic pressure at outlet plus pressure losses. And pressure losses can take place due to resistance to the flow or sudden change in direction or shape of the duct. So pressure losses in ducts occur due to friction loss, bends and fitting, etc., sudden contraction, sudden expansion. So we'll see what are the formulas for this friction loss and bend, fitting, etc. So friction loss in ducts, friction loss in ducts. So by Darcy's equation, so this you might have studied in fluid mechanics. So flow through pipe, in that you have studied by Darcy's equation, the frictional pressure loss is FL rho V square divided by 2D. Okay, you might have studied for circular pipe, FL rho V square by 2D, or in general you can write it as FL rho V square divided by 2M. Here M stands for hydraulic mean diameter or hydraulic mean depth. So here PF, F stands for frictional factor, L stands for length of the duct, rho stands for density of air, V stands for the velocity. So here I can just write this also as FL divided by M into bracket rho V square by 2, and rho V square by 2, as we know, it is a dynamic head. So PF, or the frictional loss, will be equal to FL by M into dynamic head. Okay. Now for different sections, you can calculate this. For rectangular duct, this hydraulic mean depth is general ratio of area divided by perimeter. Area of the rectangular we know A into B, perimeter we know 2 into A plus B. So I will put this into this equation and I will get a PF value. So you can see here, I will get the PF value, right? And then in the second case, for a circular duct, what will the hydraulic mean depth? It will be area divided by perimeter. This will be area of the circular will be pi by 4 d square divided by perimeter will be pi into d. So this will give you d by 4. So if you put this value into this equation, you will get the frictional pressure values. Okay. Next, the dynamic head for air is given by V by 4.04 bracket square mm of water gauge. Mm of water gauge, right? So from equation number 2, we can write FL by M into bracket V by 4.04 bracket square. So this is like in the terms of mm of water gauge. Yes, any problem? So this was frictional loss along the length of the duct. Okay, म्हणजे जसं जसं लेंथ मध्ये तुम्ही एअर पास होईल तसं काय होणार, the surface roughness of duct surface will offer resistance to the flow, and that will be counted by this formula. Now next is pressure loss due to bends and fittings, right? So previously we have seen there is a straight duct, but there are some corners. So this example is there. This is a sudden change in direction. This example is for sudden change in direction, and generally, or in applications or in practically, we do not prefer this one because it causes higher pressure drop. We go with smooth curvatures. We go with smooth curvatures. In this case, the pressure drop or the pressure drop due to bends and fittings, that will given by K into dynamic head. K stands for the constant for that particular bend. If the bend is 90 degree, K value will be more. If bend is 45 degree, the K value will be less. If the bend is circular, in that case, K value will be very, very less. So K can be taken from chart. If you want to calculate the total pressure loss, in that case, this curvature is replaced by a straight duct. So in the tables, like there are some tables for this case, we'll get equivalent length value. You will get equivalent length value. You just have to give which type of bend it is, 45, 90 degree, and it will give you the equivalent straight duct length value. Next is pressure loss due to sudden change in shape. Sudden change in shape. Okay. So first example, you can see here, there is a sudden contraction is there. And at point 2, we can see vena contracta is forming. In second example, there is sudden expansion is there, right? In both the cases, we get a pressure loss. In first case, pressure loss will be equal to K into PV3. So K constant into dynamic head at point number 3. And in and in second case, pressure loss will be equal to K into PV2. That is dynamic head at point number 2. So here always we are taking dynamic head at exit multiply by K constant, and K is taken from graphs or charts. Okay, so there are 3 types of pressure losses: pressure loss along the length of the duct, pressure loss due to bends and fittings, and pressure loss due to change in shape, sudden change in shape. Now next, important terminologies are there: aspect ratio, hydraulic mean depth, Aspect ratio is the longer length divided by shorter length. So as you can see, if I take example of rectangle, in that case, longer length is A divided by shorter length, that is A by B. If I take square, A by B will be 1, right? So generally we are preferring aspect ratio, maximum aspect ratio of 4:1. Always aspect ratio should be less than or equal to 4:1. Ideally it should be square, but most of the cases it cannot be square because of height requirements in the slab. So we are not preferring this one, we are preferring less than or equal to 4:1. Okay. Now next is very long derivation. It is actually there in the theory, but as it is an MCQ platform, I will take you swiftly through this and we'll go directly to the formula, right? But I'll explain you the theory. So what is doing here, equivalent, we are calculating equivalent diameter, right? Suppose there is this rectangular duct is there with width A and height B with length L. We want to calculate, like if I want to replace this rectangular duct by circular duct, what should be the diameter of that circular duct? That I want to calculate. So diameter of round duct, how much it should be, right? So in case one, so there are two cases. In first case, we have to assume that flow rate, that is Q value, is constant. In second case, we have to assume that velocity value is constant. Okay. So here we go with the first approach, that is flow rate is constant in the duct. Okay. So where should I put? Okay, here. Now see, previously we have known that frictional pressure loss in the duct is FL rho V square by 2M. Now for rectangular duct, what will the value of hydraulic mean depth? It will be equal to area of rectangle, that is A into B, into divided by 2 in perimeter. Perimeter of rectangle is 2 into A plus B. If I put this value into this case, I will get a frictional pressure loss. Okay, so this is what I get after putting into equation. Now if I go with the circular duct, let us say diameter is D. In that case, M value we know that is D by 4. I will put D by 4 here and I will calculate frictional pressure loss in the circular duct. Now in both the cases, the frictional loss is same. So we will equate these two equations. So we'll equate these two equations here. So we'll get equation number 5. Now with some rearrangement, I will get this equation, D raised to 5. This is a relation between diameter of equivalent or equivalent diameter and sides of the rectangle. So that if I have equivalent diameter D, so D raised to 5 should be equal to 32 into A cube B cube divided by pi square into A plus B. Okay, so always remember this formula. It was asked in the MCQ examination last year. What is the equivalent diameter formula? It should be D raised to 5 equal to 32 into A cube B cube divided by pi square into in bracket A plus B. So this was my first approach, that is flow rate of the air is constant in both the cases. Second is velocity is constant, right? So for velocity is constant, the process up to this equation number 5 is constant. Okay. After this, we have to say that this VR is equal to VC. So that velocity will get cancelled and we'll get a relation between diameter and sides of the rectangle. So see here, velocity in both the cases is same. So here this velocity and velocity will get cancelled. Ultimately, you will get the relation between diameter, that is D is equal to 2AB divided by A plus B. Okay. So it depends on the approach we are keeping in the calculation of diameter, equivalent diameter. Okay. Now we'll move towards the last point, that is duct design methods. Before that, some bullet points I have taken here for your reference. Very, very useful. We'll read it one by one. So general rules for duct design. Okay. Air should be conveyed as directly as possible to save space, power and material. म्हणजे वेडे वाकडं न जाता तुम्ही डायरेक्टली जर त्या स्पेसचा एअर सप्लाय करत असाल, सो दॅट इज व्हेरी इकॉनॉमिकल as well as it saves power and energy. Sudden changes in direction should be avoided. When not possible to avoid sudden changes, turning vane should be used to reduce pressure loss. Okay, so sudden change in direction कधी पण अशी नकोय आपल्याला. तर आपल्याला कसं ग्रॅज्युअल रिडक्शन एरिया पाहिजे. अगेन सडन असे 90 डिग्री मध्ये टर्न नकोय, कधी पण असा राऊंड कर्वेचर पाहिजे. राऊंड कर्वेचर जर पॉसिबल नसेल स्पेसच्या लिमिटेशन्स मुळे, तर तुम्ही टर्निंग वेन्स, अशा टर्निंग वेन्स असतात ते त्या 90 डिग्रीच्या डक्ट मध्ये इन्स्टॉल केल्या पाहिजे. Divergence section should be gradual. Angle of divergence should be less than 20 degrees Celsius. So this angle of divergence should be less than 20 degree. Okay. Aspect ratio should be as close to 1 possible. Normally it should not exceed 4 in any case. Air velocity should be within permissible limits to reduce noise and vibration. Okay. Duct material should be as smooth as possible to reduce frictional losses. So all that frictional head loss we calculated, it will be minimum if the surfaces are very smooth. Again, you should provide an insulation material to reduce noise and vibration. Now with this we'll go towards the duct design methods. Again, there is a long derivation for all these three methods. There is a numerical also for these methods, right? But because of online mode, we won't be able to take it, right? I will cover the theory as well as whatever MCQs will be asked. So there are mainly three methods which are commonly used for duct design. First is velocity reduction method, second is equal friction loss method, and third is static regain method. Okay, what are those? We'll see one by one. Okay. Now the first one is velocity reduction method. Okay, velocity reduction method. So in this method, the duct is designed such a way that velocity decreases and flow proceeds. That means जर तुमचा फ्लो रेट आधी जास्त असेल तर तुमचा डक्टचा साईज देखील जास्त असेल. जसं तुमचा फ्लो रेट कमी होईल जाईल तसं तुमचा डक्टचा साईज देखील कमी 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 होत जाईल. So that is with flow rate decreases means velocity also will decrease. The pressure drops are calculated for these velocities are respective branches and main duct. So see the example is given. Suppose initially this is the flow rate with velocity 600 meter per minute. आता काय झालंय त्याला एक ब्रांच आपण दिली, right? There will be another room at this end. For this we need Q1 amount of flow rate. आता काय होणार आहे, Q मधून Q1 मायनस होणार आहे and we'll get this much amount of flow rate. आता एवढ्या फ्लो रेटला एवढ्या साईजच्या डक्टची गरज लागत नाही. For that we required again calculation of duct and we'll get this size. Again we have another branch Q2 and we have Q minus Q1 minus Q2, this last flow rate. For this again we have to design the duct. So the duct sizes are determined for assumed velocities and known quantities of air to be supplied through respective duct. म्हणजे कसं असतं की या वेलोसिटीला आणि या फ्लो रेटला किती क्रॉस सेक्शनल ऑफ डक्ट पाहिजे ते फिक्स असतं, फिक्स आहे स्टँडर्ड मध्ये. जस्ट यू हॅव टू सिलेक्ट लेंथ अँड इट विल कॅल्क्युलेट अँड देन यू हॅव टू कॅल्क्युलेट विड्थ. फक्त तो एरिया तेवढा आला पाहिजे. ओके, right? So with reduction velocity, area also will decrease. Next is equal friction loss method. Okay, generally this is not preferred in main calculations. People go with static regain or velocity reduction method, but we'll see for theoretical part. So in this method, the frictional pressure drop per unit length of the duct is maintained constant throughout the duct system. Okay, and the value is also very common in industrial or commercial application, that is 0.08 mm of water gauge per meter of duct length. Okay, this value is constant, and I have used the softwares related to duct design. In that also this value is maintained constant, 0.08 mm water gauge per meter length of duct. The procedure is to select the suitable velocity in the main duct from the sound level consideration. Knowing the air flow rate and velocity in the main duct, the size and the friction losses are determined from the friction chart. Okay, so we are assuming there is equal friction losses taking place per meter length of the duct. Accordingly, we are calculating the duct sizes. Okay, so anyone who want to pursue career in the HVAC, they will come across ESP sheets, external static pressure sheets, in which we calculate the duct sizes. From duct sizes, we calculate the power required to drive the fan in the duct. Okay, ESP चं कॅल्क्युलेशन करतो आपण, टोटल प्रेशर ड्रॉप करतो, त्यातून आपण काय करतो, किती साईजचा फॅन लागणार आहे, ब्लोअर और फॅन लागणार आहे हे कॅल्क्युलेट करतो. साईज ऑफ द फॅन वर आपल्याला ठरतं की त्याला किती पॉवर लागणार आहे, पॉवरवरून कळतं आपल्याला की ते आपल्यासाठी किती युनिट एनर्जी consume होणार आहे. So ESP calculations are very important in the HVAC field. And the last one here, it is static regain method. Static regain method means here in this case, whatever loss, so we have studied there are two pressures. One is static pressure, another is dynamic pressure. So in this method, it is assumed that if there is a loss in the dynamic head, it is covered or it is regained by static pressure. If there is a loss in static, it is regained by dynamic. So all the total amount of the pressure remains constant in the system. Okay. So for the perfect balancing of the air duct layout system, the pressures at all outlets must be same. This can be done by equalizing the pressure losses in various branches. This is possible if the friction loss in each run is made equal to the pressure gain to the reduction in velocity. म्हणजे काय म्हणता येते की जर कशा एकामध्ये रिडक्शन झाली तर आपण असे अज्युम करायचं की दॅट विल द प्रेशर गेन ड्यू टू रिडक्शन इन वेलोसिटी. डायनॅमिक हेड जर कमी झालं रिडक्शन इन वेलोसिटी ना, that will be increase in static pressure. Okay, and mostly people refer this static regain method. Actually this is just a very short explanation, or the introduction is there. Actually how it is done, it is explained with the help of derivations, which is not included. Anyway, what are the advantages? It is possible to design long run as well as short run for complete regain. It is sufficient to design main duct for complete regain. Okay, so again I will repeat what is happening in static regain. So see, I have explained with the help of diagram. When the balloon or filled balloon is closed, air is acting a static pressure. So this is static pressure. When I puncture the balloon, air will come out. It will come out under the pressure of dynamic pressure. So whatever reduction in dynamic pressure is taking place in this case, or reduction in static pressure is taking place, that will be regained in the dynamic head. म्हणजे काय होतंय, स्टॅटिक प्रेशर हळूहळू कमी होत जाणार पंक्चर झाल्यानंतर आणि डायनामिक हेड वाढत जाणार. सो दॅट इज रिगेन बाय डायनामिक हेड. But total pressure, if you see, total pressure will remain the same. Okay, so thank you, that was it. Once again I will revise because most of it was theoretical part, so that is why I have taken it at fast space, but still I will prepare all the slides. So we are at this chapter air distribution systems. Here I started with the example of AHU. Okay, then I have given you the requirements of a duct system, right? So a trade-off is required between operating cost and initial cost. Then we saw the classification of ducts. Then we have seen what is the material used in the ducts, what are the shapes used for the ducts. Then there are two types of pressure, static pressure and dynamic pressure. We have seen, or we have applied mass balance and Bernoulli's theorem for the ducts. Then we have calculated frictional pressure losses for various cases, like for straight length, then for bends and fittings, and then for sudden contraction and sudden expansion. We have seen how to calculate equivalent diameter from a rectangular duct. So there are two approaches. First is constant volume flow rate approach. Second is constant velocity approach. Then last was design methods. There are three methods: velocity reduction method, equal friction loss method, and static regain method. And last but not the least, here these are the general guidelines. Air should be conveyed directly possible. Sudden changes should be avoided. Divergence section should be smooth as possible. Aspect ratio should be always less than or equal to 4. Air velocity should be within permissible limits, and duct material should be as smooth as possible. So any doubt up to this point? Any doubt? Any doubt? Okay. So with this, our chapter number 6 is concluded. And with chapter number 6, I can say that this whole subject, refrigeration and air conditioning, is also concluded. For your practice purpose, I have given one mock test. Please try to solve it. You can try it as many times as you want. Solve it so that your practice will be more. Okay. Now, yes, again, the study material will be uploaded soon in that study sheet. You can refer to the study material also. I will upload this lecture to the YouTube. You can refer to this lecture from YouTube also. Okay. So I wish you very all the best and all the success in the university examinations. If you have any doubt at any point of time, you can call me. I will help you. Okay. So rack is the subject that will decrease your marks. Remember, other subject will give you good grades. But when it comes to rack, it requires understanding. If if your understanding is not good, then your marks will be reduced. So if you see last year, if you can ask your seniors also, most of the students त्यांचं ग्रेड किंवा CGPA कमी कशामुळे येतो तर रॅक मुळे कमी येतो because their basic understanding is not clear. If your basic understanding is clear, if your practice is good, then definitely rack will give you good grades. Right? So with this, we'll stop today. If possible, I will take a practice session if required by you. If you ask, then I will take a practice session. Like we'll practice some MCQ related to refrigeration and air conditioning. So please enter your roll numbers in the chat box and then we can stop. Thank you.